Hello, novice statisticians. Welcome back to our discussion of correlation. And now we are in part B, 9B. Okay, going to slide 2. So, what do what does correlation mean? In the first part of the lesson, we looked at correlation graphically, we looked at it algebraically, we looked at how it might look if you were calculating it in Excel. Okay? But it's important to know, one thing that's important to know, and a mistake that novices often make, is this idea that correlation equals causation, and it doesn't. We cannot say that reading level causes an exam score, or temperature causes ice cream sales, just from the correlation alone, even though we might think it's true, right? We might think that if a person reads better, they're going to do better on their reading exam, and we're right most of the time. But we can't say that one causes the other if we only have a correlation to go with. Okay, it just tells us that two variables are related to each other. It doesn't tell us why or how. So there are a few little examples here. It said, let's say you read that as people grow older, they tend to store their socks flat rather than rolled up. So does that mean that if I roll my socks up, that's automatically going to make me younger? No. Over the years, the autism rate has risen, and so has the rate of organic food sales. Does organic food cause autism? No. And when the pilot says fasten your seatbelts, and then it starts to bump, fastening you're in a plane, then it gets bumpy. Fastening your seatbelt does not cause the plane to start bouncing around in the air. And finally, just because the boss is getting nasty emails every time he leaves your cubicle doesn't mean that it was you. Okay, correlation does not imply causation. So, possible explanations for a correlation. It could be that one of the variables is causing the other. We might have it backwards, right? So, upcoming bumpy air leads to the pilot saying fasten your seatbelt, not the other way around. There could be some third intervening variable that's influencing both variables. This is also called a spurious correlation, when there's some third thing that relates to both things, and the two things don't relate to each other, really. Okay. Also, it could be that our sample isn't representing the population well, and the correlation doesn't really exist. But that last one we can address statistically. Okay. So basically, how confident are we that our correlation isn't zero? All right. So we've drawn a sample, and as usual, we can calculate a statistic. We can calculate this Pearson's R. But how do we know that the population from which we drew this sample, that the correlation in the population isn't zero, and that our sample is just sampling error? Okay, it's just chance. It's just an idiosyncrasy of the sample that we drew. So our null hypothesis is that there's no correlation between our two variables, or R equals zero. And our research hypothesis is that there is a correlation between our two variables, that the two variables are related, that R is not equal to zero. It's always possible that we're going to misrepresent the population. Okay, so this figure shows if you were drawing samples of 50, this might be the sampling distribution you'd get when the correlation is zero. So sometimes you'd get a positive correlation, sometimes you get a negative correlation, but um, the distribution of your samples would center on 0. So that means basically we can test this similar to how we have done before. We calculate the chance that I'm looking at slide 7. We calculate the chance that a statistic will occur, a particular statistic would occur, a particular R would occur, given the null is true. And the p-value for the correlation is the probability that a correlation this extreme or more extreme, remember correlation varies from 1 to -1. This extreme or more extreme, closer to 1 or closer to -1, would occur due to sampling error when the null is true, when the real correlation is 0. So if we were doing this by hand or with Excel, we can find the critical values of the correlation. We calculate the R, and then we can find the critical values by looking up the degrees of freedom. We're going to use n-2. We have 2 variables. Okay. And you look on table E2 and it has your list. With a sample size of 50 and an alpha of 0.05, the critical values are 0.273 and -0.273. So a correlation more extreme than these, our statistic more extreme than these, would lead us to reject the null hypothesis. Okay? If you calculated a correlation more extreme than plus or minus 0.273, 5% of the time, the true correlation of the population could be 0, but we're willing to take that chance. Slide 9. So if we have a value more extreme than the critical value, we conclude this would be rare enough that we'll reject our null. Okay, in practice, this means we conclude that the correlation isn't 0, that there is a correlation between the 2 variables, and we're willing to be wrong 5% of the time. So does this kind of sound familiar? I hope so. All right, let's look back at our ice cream example. So slide 10. Our temperature and ice cream sales correlation was 0.96. That's what we calculate if we go through the steps in Excel, or God forbid, just with a calculator. Our sample size is 12, so our degrees of freedom is 10, n-2. We look up at the table the degrees of freedom of 10 and find that the critical value is 0.576. Okay, since our correlation is larger than 0.576, 0.96 is larger than 0.576, we can reject our null and conclude that our non-zero correlation isn't due to sampling error. So it's not just due to only those 12 days. Those 12 days, we're saying those 12 days were not idiosyncratic. They're pointing to a trend. You actually do sell more ice cream when the weather is warmer. Okay, software might tell us that P is less than 0.0001 for this correlation. That means that there's less than a 0.01% chance of a value as extreme as 0.96 occurring due to chance when there is no correlation in the population. Okay, so slide 11. Let's look at how this would look in SPSS. So I imported the ice cream data from Excel to SPSS. I changed it a little bit. There was that degree sign. I deleted the little degree circle. Okay, we don't want to confuse SPSS with non-standard characters. Okay, and yeah, but other than that, and I took away the dollar signs. I'm sure SPSS could handle it, but again, I'd rather just send just plain numbers to SPSS. Okay, so you know how to import from Excel to SPSS, right? Right, you got that now. And what you would do is you go to Analyze, slide down to Correlate, and choose bivariate, which means we're correlating all pairs of variables. And then you move your variables into the variables box, and I've already done that in that picture. And if you could go to Options, for missing data, select exclude cases list-wise, okay? And this doesn't matter really when you only have two variables, but as your research gets more and more complicated, you might end up with 5, 10, 15, 20 variables that you're looking at the correlations. Exclude cases list-wise, so you're only including those who have data for all of your variables. Okay. And slide 12. Okay, so this is the output that you would get. You'll get a correlation matrix, and that means you have rows and columns. And on the rows, there are each of your variables, temperature, sales. On the columns, there are also each of your variables, temperature, sales. The first box is going to be temperature. And does that correlate with temperature? Yes, it does. In fact, it correlates perfectly with itself. So you get 1. And then you'll have, in that first row, temperature. If the first row is temperature, temperature and ice cream. And there we see 0.958, which rounds to 0.96. Okay. And then you get the mirror image. Sometimes you'll see a correlation matrix and it looks like a triangle because they're only showing you the bottom half, because the top half is going to mirror the bottom half with this correlation matrix, the way it's laid out. Okay, so here's how I would write about this. Here's the language I might use. Ice cream sales and temperature were strongly positively correlated. Okay, and in your book, it talks about what is considered a strong, a moderate, and a weak correlation. Okay, they were strongly positively correlated. And parentheses, R equals 0.96. The relationship was statistically significant. Okay, parentheses, P less than 0.001, because there it says P, equal to 0.000. We know it's less than 0.001. We reject the null hypothesis that the correlation in the population is 0. We conclude that when the temperature is high, ice cream sales also tend to be high. Okay, if they had been negatively correlated, maybe people drink less tea when it's hot or eat less soup or something like that. So if we were looking at sales of hot tea and temperature, they would be negatively correlated. And we would conclude that when the temperature is high, the sales of hot tea tends to be low. Okay, that's a negative correlation. All right. So let's talk about statistical significance for a moment. Slide 13. Statistical significance does not mean that the correlation is strong. Okay? Strength is measured by R. Okay? It doesn't mean the correlation is important. Okay? Because it could be two things that you don't care if they correlate together. It does mean that the correlation is likely to be non-zero in the population. So the correlation is or isn't due to an error of sampling. Okay, slide 14. So now with correlation, the nice thing about Pearson's R is you can use the same formula for a bunch of different kinds of data, but you call it different things. So you would call it point biserial if one variable is dichotomous, and you would call it phi if both variables are dichotomous. Okay, but basically you do the same procedure. If the variables are ordinal, if one of the variables is ordinal, it's probably better if you do ranks. And that I talk about in the appendix, okay? And it's also in your textbook. You'd use Spearman's rule. Okay, so decisions. What type of data do I have? Do I have continuous data for both variables? Then you use Pearson's R. Okay, do I have continuous data for one variable and dichotomous or yes, no type data for the other? Then I use Pearson's R formula, but report it as a point biserial correlation. Dichotomous for both variables, You use Pearson's R formula, which means in SPSS, you're basically going to be doing the same thing for all of these, but you report it as phi. And if either of the variables are ordinal, you would convert the scores to ranks and then use Pearson's R formula with the ranks and report it as Spearman's rho. Again, there's more information about that in the appendix, as well as kind of like something for you to think about in the appendix. But that's all for now for our lesson on correlations. And it's really gonna, these lessons really set a good foundation for us for when we're learning about regression next time. Okay, I hope you enjoyed that, and I hope you have a really good week. Bye-bye.